Hello everyone, it's Jay, and today we'll be going through problem 2 on your pre-workshop, which states that we have a borohydride sample containing only boron and hydrogen, and we're told that it's combusted in pure oxygen to make the products BO3H3 and B2O3. Now, we're told that it requires 23.9985 grams of pure oxygen, and that when we do this reaction, we get 17.4075 grams of B2O3. Question asks, what is the empirical formula of the compound? So I know this looks like a more challenging problem. It looks a little different, and we don't have a carbon-containing starting problem, a molecule. We don't have the grams of our unknown compound, but as you'll see as we go through this video, and we go through the bubble diagram combustion analysis process, it's actually quite similar to all the other combustion analysis problems that we've done. So let's start by writing our combustion analysis reaction. We know that we have B and H, and it's combusted in pure oxygen. We don't know the molar ratios of B and H. We're looking for that. So let's call that BXHY. Again, we combust in pure oxygen. And now we yield BO3H3 and B2O3. So let's start with what we know. Well, we're given the mass of oxygen. So we know that we have 23.9985 grams of O2. And we're given the mass of B2O3. So we know that we have 17.4075 grams of B2O3. Now let's try to go to moles and let's break down these grams. So starting with oxygen, we know that the molar mass from the periodic table is 31.9985 grams per mole. So we have 0.75 moles of O2. If oxygen is in a 2-to-1 ratio in O2, so 2 oxygens per molecule of O2, we get that we have 1.5 moles of oxygen. Now let's do the same kind of analysis for B2O3. We're given the grams. Let's go to moles. We know that this is 69.63 grams per mole by the periodic table. So we have 0.25 moles of B2O3. Now here we can actually draw two arrows. We know that boron is in a 2-to-1 ratio. So we have 0.5 moles of boron. And we know that oxygen is in a 3-to-1 ratio, so we'll say that that's oxygen. And that means we have, draw our bubble, 0.75 moles of oxygen. Great, so if we start with 1.5 moles of oxygen and 0.75 moles of oxygen go to B2O3, then what we also know is that the other half, or 0.75 moles of oxygen, go to BO3H3, because all of these moles of oxygen must go to BO3H3 and B2O3. So that accounts for our 1.5 moles. Now, we want to get borons and hydrogens, so let's do that. We know that in BO3H3, our hydrogens and our oxygens are in a 3-to-3 or 1-to-1 ratio, so we also have 0.75 moles of hydrogen. And we know that our boron is in a 1-to-3 ratio, so we have 0.25 moles of boron. So now we have all of our moles. Now we can work on our molar ratios. So the only hydrogen-containing compound is BO3H3, and it has 0.75 moles of hydrogen. So all of that hydrogen must come from BXHY. So we can erase our Y and we can put a 0.75 for now. Now our boron comes from two sources, but we see we have 0.25 moles of boron from BO3H3, 0.5 moles of boron from B2O3, so we have a total of 0.75 moles of boron. So let's put another 0.75 right there. Now we've replaced our x and y with numbers, so we have B.75, H.75. We obviously cannot keep them as decimals, so what we do is we divide by our greatest common factor, which is 0.75, and we get B1H1, or we get rid of any one subscripts or coefficients. BH is the empirical formula of our compound. Thank you so much for watching.